This module discusses the counting rules used in probability estimates and gives a brief overview of the set theory.
After studying this module, you shall be able to learn how to count the number of outcomes of an experiment and apply the rules of permutations and combinations to it. It will help you understand the concept of binomial coefficient, which is used to explain binomial theorem in later parts of statistics. The elementary set theory has been discussed, which will facilitate the understanding of probability. To understand the importance of counting rules, try out these questions. If 5 books are to be arranged in a bookshelf, then what are the different possible arrangements? A multiple choice paper has 15 questions and every question has 4 options. In how many ways can an exam be completed? These questions require us to identify the possible outcomes, which can be comfortably solved by using the counting techniques. The rules that we learn in this module facilitate the ordering and selection problems. But the challenge comes in deciding which counting method the problem is defining. How many possible outcomes are we choosing from? Are repetitions allowed? Does ordering matters or not? These questions are important to be answered before deciding the rule that has to be applied.
The problems like these can be easily seen in our daily life and could be comfortably solved by using the counting techniques developed. The rules that we learn in this module facilitate the ordering and selection problems. But the challenge comes in deciding which counting method the problem is defining. How many possible outcomes we are choosing from? Are repetitions allowed? Does ordering matters or not? These questions are important to be answered before deciding the rule to be applied to the problem.
The counting of the number of outcomes of an experiment will be fundamental to the study of probability. The basic rule states that if one experiment can result in m possible ways, and if another experiment can result in n ways, then the two experiments together can be performed in mn ways. Suppose two balls are selected from a bag containing 5 balls marked A, B, C, D, and E without replacement. Possible outcomes are AC, DE, and so on. Listing all the possible outcomes to find the total number of outcomes will be an inefficient exercise. The first draw has 5 possible balls to choose from, and the second draw has just 4 balls left to it. Therefore, we get 20 possible cases. Now consider an example of selecting elements with replacement. Suppose you want to choose a 4-digit PIN code for your debit card and each digit takes a number from 0 to 9. Then first digit has 10 possible numbers to select from and so has second, third, and fourth digits with replacement case. Thus, the total possible choices of a 4-digit PIN code are 10 multiplied by 10 multiplied by 10 multiplied by 10 is equal to 10,000. Therefore, in general, if we have n objects and we select r of these with replacement, and order is not important, then there are n raised to the power r possible outcomes.
Let us take another example. Suppose 15 candidates are interviewed for 3 vacant positions. In how many ways can the selection be made? Since one person can fill only one position, therefore the selection is without replacement. The first post can be filled by any of the 15 candidates. The second post has 14 persons left to it, and the third post has 13 persons left. Therefore, the total number of ways are 15 multiplied by 14 multiplied by 13, which is equivalent to 2730.
To understand permutation, consider the following question. How many different ordered arrangements are possible of letters x, y, and z. The answer would be 6 outcomes as x, y, z, z, x, y, z, y, x, x, z, y, y, x, z, and y, z, x. Each of these 6 outcomes is a permutation of a set of 3 letters. We can define permutation as follows. Suppose a set has n elements and an experiment consists of choosing k elements out of total without replacement. It implies that each outcome consists of k elements in the order selected. Each outcome is then called a permutation of n elements taken k at a time. It is denoted by p n k. It is equal to n factorial divided by n minus k factorial. The order of the elements matters in a permutation. Let us take an example to understand permutation. Suppose, in a baseball game, 3 players are to be selected out of 9 to play the roles of the pitcher, first base hitter, and second base hitter. The total possible ways to select 3 players is given by substituting the values we get. The total possible ways are 504 ways. The order in which the players are arranged does matter in a permutation. It implies that player arrangement 1, 2, 3 is not equal to 3, 2, 1. Those same 3 players have been used to make these 2 arrangements, but different ordering implies that they are different permutations. Permutations are usually used in the cases where ranking of people is important. Example, choosing a cricket team where players are to be chosen for captaincy, bowlers, opening batsmen, etc. To understand combination, consider the following question. How many subsets of size 2 can be obtained using letters x, y, and z? The ordered arrangements, permutations, would be xy, yx, zy, yz, zx, and xz. However, if unordered arrangements are observed, then xy is equal to yx and so on. Thus, there are only 3 unordered arrangements combinations, namely xy, yz, and zx. We can define it as follows. Suppose a set consists of n elements, then each subset of size k chosen from it is called a combination of n elements taken k at a time. The number of such subsets is denoted by CNK or NCR. No 2 combinations can consist of same elements because the subsets with same elements in it are considered to be the same combination. In other words, we are simply asking for the total number of subsets of size k that can be selected from a set of n distinct objects. In the above case of selecting 2 elements out of x, y, and z, 2 different permutations xy and yx both correspond to the same combination xy. There are 6 total permutations and 3 combinations. We can think of permutation as being constructed in 2 steps. First, a combination of k elements is chosen out of n, a combination, and second, these k elements are arranged in specific order and each ordered arrangement is a permutation. The ordered arrangements of k elements in the second step can be done in k factorial ways. In our example, k is equal to 2, as subset of size 2 was required, and each combination of elements can be arranged in 2 factorial ways to make permutations from the same elements. Thus,
let us take some examples to understand combinations. Consider the word pepper. Now find out the number of words that can be formed by arranging these letters. Note that if the 3 P's and 2 E's are distinguished from each other, then there are distinct letters and total number of words would be 6 factorial. Here ordering matters and there are 6 factorial permutations. However, if the 3 P's and 2 E's are not distinguishable, then permuting P's among themselves and E among themselves for any single permutation would not change the result. For example, in permutation P1, E1, P2, P3, E2 are, if places of P1 and P2 are interchanged, then also the word is the same. These three P's can permute in 3 factorial ways and the E's can permute in 2 factorial ways. That is, all 3 factorials into 2 factorials permutations are of the form paper. Hence, there are 6 factorials divided by 3 factorial multiplied by 2 factorials, which is equal to 60 arrangements or combinations possible of the word paper. In how many ways can the numbers 1, 2 up to 5 can be arranged so as to make a 5-digit number like 1, 3, 2, 4, 5 or 4, 3, 5 to 1, etc. The answer would be 5 factorial. 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. However, if the question is such that the first two digits are 1 and 2 in any order and the other three digits are formed using 3, 4 and 5 in any order, then the answer would be 2 factorial multiplied by 3 factorial. Numbers 1 and 2 can be arranged in two ways, 1, 2 and 2, 1. Therefore, 2 factorial and numbers 3, 4 and 5 can be arranged in 6 ways or 3 factorial ways. The total number of cases would be 2 factorial into 3 factorial. A chess tournament has 10 players, 4 Indians, 4 Sri Lankans and 2 Chinese. If the result of the tournament just lists the nationalities of the players in orders in which they are placed, then how many such arrangements are possible? In this case, the order is important and thus the permutation is used. The total possible arrangements are 10 factorial. If all the players are distinguished from each other and the nationality is not considered. However, like the previous example, if we allow the 4 Indians, 4 Sri Lankans and 2 Chinese to permute among themselves, then the total number of arrangements would be 10 factorial divided by 4 factorial multiplied by 4 factorial multiplied by 2 factorial, which is equal to 12,600 arrangements.
Again, take the example of a baseball game in which 3 players are to be selected out of 9. It is different from the case of permutation, as now ordering is not important. It implies that player arrangement 1, 2, 3 is equal to 3, 2, 1. Thus, the total possible ways are given by, after substituting the values we get 83 ways. It is like dividing the number of permutations by 3 factorial multiplied by 3 factorial is the number of possible arrangements of 3 players. So permutations 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, and 3, 1, 2 all correspond to a single combination 1, 2, 3. Let's understand the concept of binomial coefficient. If n is a positive integer and we find the value of x plus y raised to the power n, then each term of this expansion will be a product of x's and y's with an x or a y coming from each of the n factors of x plus y. Take for example x plus y raised to the power 4. The total number of terms in this expansion would be 2 raised to the power 4 is equal to 16. The expansion of x plus y raised to the power 4 is given by, there are 5 terms in the expansion and the coefficients of the terms are 1, 4, 6, 4 and 1 respectively. To understand the meaning of these coefficients, take the term x square y square. It has coefficient 6, implying that this product of x and y occurs 6 times in the expansion. In other words, there are 4 by 2, see 4 2 number of ways in which we can choose the two factors providing the y. Similarly, the coefficient of xy raised to the power 3 is 4 by 3 is equal to 4 ways in which we can choose three factors providing the y. This leads us to generalize the above example to imply that if n is a positive integer and we multiply out x plus y raised to the power n term by term, then the coefficient of x raised to the power n minus k, y raised to the power k is given by n by k. It is the number of ways in which we can choose k factors to provide with y. The number n by k is termed as the binomial coefficient. The properties of binomial coefficients are as follows. Firstly, for all n, n by 0 is equal to n by n, which is equal to 1. This follows from the result that 0 factorial is equal to 1. And secondly, for all n and all k is equal to 0, 1, 2, so on up to n by k is equal to n by n minus k. This result simply means that selecting k elements to form a subset just like selecting n minus k elements from the complement of the subset. Now we will move to the concept of set. A set can be simply understood as a collection of distinct objects. If set A is defined so as to contain first 5 natural numbers, then it is sufficiently well described to make clear that the numbers 13 and 14 are not in the set. If an object belongs to a set, then it is said to be an element of the set. Here, 2 is referred to as an element of the set. In certain considerations, the totality of elements pertaining to that discussion or consideration can be identified and described. This set of all possible elements of a consideration is called the space. For example, suppose that the number of heads in 3 tosses is denoted by x, then x can take values 0, 1, 2, and 3. Thus, the space of this experiment would be D is equal to 0, 1, 2, 3.
Sets should not be mistaken to just mean collection of numbers. If a set is defined over a one-dimensional space, then it is a set of numbers, say x. The notation C is a set of x elements such that x lies between 0 and 1. This would mean that C is one-dimensional set of points x where x takes the value between 0 and 1 inclusive. However, set A is such that contains values of x and y such that the value of x lies between 0 and 1 and the value of y lies between 0 and 2, and this is understood as a two-dimensional set of points x and y that are interior to or on the boundary of a rectangle with opposite vertices at 0, 0 and 1, 2. Similarly, sets could be defined for n-dimensional spaces. Thus, it implies that language of sets of points is more convenient and complete than understanding the sets as just pertaining to numbers. In certain considerations, the totality of elements pertaining to that discussion or consideration can be identified and described. This set of all possible elements of a consideration is called the space. For example, suppose that number of heads in 3 tosses is denoted by x, then x can take values 0, 1, 2 and 3. Thus, the space of this experiment would be a set D such that it contains elements 0, 1, 2 and 3. The concept of space will be often referred to in understanding the operations of set theory. Now we will discuss the elementary algebra of sets, which facilitates the understanding of the concept of probability.
Let's discuss different types of set. Subset of set, that is, If each element of a set A1 is also an element of set A2, then set A1 is a subset of set A2. As shown in the figure, the set A1 is completely contained in set A2, implying that all the elements of set A1 are present in set A2. Null set. If a set A has no elements in it, then A is an empty or null set. This is indicated by writing A is equal to phi. An example would be defining a set which contains the negative numbers obtained in roll of a die. As the roll of die yields only positive numbers, thus this set has no elements and it is a null set. Finite set. These are those sets that have finite number of elements and are called finite sets. Infinite sets are those sets that have infinitely many elements. It could be of two types, countable and uncountable. An infinite set A is countable if there is a one-to-one correspondence between the elements of the set and the set of natural numbers 1, 2, 3, and so on. Examples could include the sets of positive integers, odd integers, prime numbers, etc. On the other hand, a set is uncountable or infinite if the elements of the set are neither finite nor countable. Take for example the set x is equal to. Here the numbers in the interval 0, 1 are infinite and cannot be attached as having one-to-one correspondence with natural numbers. Let S denote a space and let A be a subset of S, that is, A is a subset of S. The set that consists of all the elements of S that are not the elements of A1 is called the complement of set A with respect to space S. It is denoted by A raised to the power C. In the above figure, the rectangle represents the space S and A is its subset as all the elements of A are also present in S. The shaded area includes all those elements which are present in S but not present in A. Thus, it is complement of A raised to the power C. Take for example that a space includes the result of roll of a die. Then S is equal. The properties of the complement of a set are as follows. As the space contains all the possible elements, thus complement of a space has no element in it. In particular, S raised to the power C is equal to phi. It implies that phi raised to the power C is equal to S. Moreover, it should be noted that A raised to the power C raised to the power C is equal to A. If A1 and A2 are two sets defined in space S, then union of A1 and A2 is defined to be the set that contains all the elements that belong to A1 alone or A2 alone or both. In other words, union of sets includes all the elements that belong to at least one of the sets. The union of sets A1 and A2 is denoted by A1 union A2 and it is depicted in following Venn diagram. In the figure, the shaded area is union of sets A1 and A2. Take for example, define the sets B1 is equal to 1, 2, 3, 4, 5, 6 and B2 is equal to 3, 6, 8, 10. Then the union of sets has the following properties. 1. A1 union A2 is equal to A2 union A1. 2. A1 union A1 is equal to A1. 3. A1 union A1 complement is equal to S. 4. A1 union phi is equal to A1. 5. A1 union S is equal to S. Lastly, associative property. It states that for three sets A1, A2, and A3, A1 union A2 union A3 is equal to, within brackets A1 union A2 union A3 is equal to A1 union within brackets A2 union A3. If A1 and A2 are two sets defined in space S, then intersection of sets A1 and A2 is defined as a set which contains the elements appearing in both the sets. It is indicated by writing A1 intersection A2, and it can be depicted in the following Venn diagram. In the figure, the elements included in the shaded area are present in both sets A1 and A2. Thus, it is the intersection of sets A1 and A2. Consider a set A1 defined so as to include multiples of 2 less than 20. A1 is equal to 2, 4, 6, 8, 10, 12, 14, 16, 18. Set A2 is defined to include multiples of 3 less than 20. The intersection of sets has the following properties. 1. A1 intersection A2 is equal to A2 intersection A1. 2. A1 intersection A1 is equal to A1. 3. A1 intersection phi is equal to phi. 4. A1 intersection A1 complement is equal to phi. 5. A1 intersection S is equal to A1. 6. If A1 is a subset of A2, then A1 intersection A2 is equal to A1. Lastly, for the three sets A1, A2, and A3, following associative property should be satisfied. A1 intersection A2 intersection A3 is equal to, within brackets A1 intersection A2 intersection A3 is equal to A1 intersection within brackets A2 intersection A3. After understanding the basic concepts of set theory, let's define the Morgan's law. According to this law, for any two sets A1 and A2, the following holds. These properties can be easily depicted through Venn diagrams.
Let us now recapitulate what we have learned in this module. The basic principle of counting states that if one experiment can result in m possible ways and if another experiment can result in n ways, then the two experiments together can be performed in m into n ways. The permutation of n objects with k at a time means selecting k elements out of n in a particular order. Combination of n objects taken k at a time implies selecting a subset from L elements of the size k. The number of ways in which subset of size r can be chosen from n elements is denoted by n k and is called binomial coefficient. The set is a collection of distinct objects. In each element of set A1 is also an element of set A2, then set A1 is a subset of set A2. If a set A has no elements in A, then set A is an empty or null set. The sets that have finite number of elements are called finite sets, while others have infinitely many elements. The set that consists of all elements of S that are not the elements of A1 are called the complements of set A. If A1 and A2 are two sets defined in space S, then the union of A1 and A2 is defined to be the set that contains all the elements that belong to set A1 alone or set A2 alone or both. If set A1 and set A2 are two sets defined in space S, then intersection of sets A1 and A2 is defined as a set which contains the elements appearing in both the sets.